Alright, so we are looking at basically four things here.
Don't write so hard either.
We're looking at Kastolite 30, Portland cement, SiO2, which is silica, Al2O3, which is aluminum oxide, Fe2O3, which is iron oxide, CaO, which all y'all have heard me say several times. This is calcium oxides. Looking at MgO, which is magnesium oxide, TiO2, which is titanium oxide. Also an Na2O and a K2O. Alright, now we are going to be looking at these for Kastolite 30, in which we're trying to find a home recipe for. Portland cement, I told you this is coming out of left field. Alright. We're also going to be looking at aluminum oxide blast material. Okay, and one more, Roman cement and Roman concrete. The difference between cement and concrete is concrete has aggregate in it. Cement's the glue that holds it all together. All right. This is potassium oxide, and this is a sulfate. I can't remember which one it is. Whatever Na is on the periodic table. For Kastolite 30, this is what we have. As far as silica, it's got anywhere from 33.5 to 37.5% of silica, which is silica sand. As far as aluminum oxide, which is actually, it's the alumina, is what they're talking about. There's a difference between the alumina, and I'll tell you the difference between the aluminum oxide blast material and the alumina that everybody thinks about as the white fluffy stuff. This has got 55.5 to 59.5%. That is a high alumina content, but I have seen it all the way up to 70s. Over half of it is aluminum oxide. Iron oxide has got 0.5 to 1.0%. Low iron oxide, that's good. That's good. Calcium oxide. We have 3.5 to 5%, which is very little calcium oxide. I was actually wish I had paid attention to these numbers before, because that bothers me a little bit that it's that low. Magnesium oxide, we got 0.1 to 0.4. And you'll know why I'm listing all these here in a minute, okay? Titanium oxide, we've got 1% to 2% of titanium oxide. And as far as these two, the potassium, and I'm not sure what this one is, but these are just alkalines is all they are. They're just alkalines, and I've got to figure out what the alkalines actually do, and I think it has to do with the curing process. I think it's pretty much it. There's only a half to 1.2%. All right, now, out of all these that Kastolite has in them, Portland cement has 5 of these ingredients. When it comes to silica, Portland cement has 17 to 25%. Not as high. Okay? For aluminum oxide, it's got 3 to 8%. Nowhere near it. Iron oxide, 0.5 to 6%. Calcium oxide, 60 to 67% calcium in Portland cement. See, I thought Portland cement was a clay-based substance, and it is not. It is a calcium-based substance. Which led me to another question, and I'll answer that in just a minute. Magnesium oxide, we've got 0.1 to 4%. Basically the same. Magnesium oxide. Titanium oxide, no, it has no titanium oxide in it at all, and it has no alkalines in it at all. So already we have some similarities here. Now, I told you this was concerning because I thought that this was going to be a calcium-based substance, and it's not. It's an alumina-based substance, which makes sense because alumina is probably one of the best refractories out there. Like, but wait a minute now. So I can increase this, and I can increase this. And these are pretty much the same, but how do I decrease the calcium oxide down to the Kastolite level? Well, when I increase this, this is going to drop. Anytime, if I were to increase any of this, all this is going to drop somewhere. Okay? So if I increase the silica and I increase the aluminum oxide, this is going to drop substantially because of how much is there. Still going to be a good bit, but I'm not so much concerned about it because it's calcium. Where am I going to find titanium oxide? I mean, it's oxidized titanium. Titanium's expensive. So let's go over here to the aluminum oxide blast material. Okay? So the aluminum oxide blast material for silica has 0.83%. Not much at all. For the aluminum oxide, it has 95.69%. Which tells you why it's aluminum oxide blast material. It's primarily aluminum oxide. Iron oxides, it has 0.28%. Calcium oxide, there is none. No calcium oxide whatsoever. Magnesium oxide, 0.29. Now we got the titanium oxide, in which Portland cement has none. Aluminum blast material has 2.66%. And the aluminum oxide blasting material does not have any alkalines in it together. So between these two, in which I can use this as an aggregate, I have every bit of material. I'm bringing this number up because number one, I'm using it as an aggregate because it's big enough to use as an aggregate. And number two, I'm adding it together. I'm bringing this number up, and I'm bringing this number up. Very little silica, very little. I can add more silica to it. So already this is dropping. Roman cement is comprised of CaO, which is calcium oxide, basalt rocks as an aggregate, but that is not the kicker. So this has got a lot of calcium oxide, just like Roman cement does. This uses an aggregate, just like Roman cement does. So why was Roman cement so much superior to Portland cement? What is it about Portland cement that breaks down after about 50 years, but Roman cement's been around for thousands of years and still stands tall? How is it so refractory? How did it survive? How did Pompeii survive the way it did? How did Herculaneum survive the way it did? Because of the calcium oxides. That's pretty much the reason right there. The basalt aggregate, that's a volcanic stone right there. So, I thought this was a decadent. I thought that was a decadent that made it dry out faster, and that is not true. This is one reason, and here's the other reason. these two together is what makes Roman cement so much more superior than the concrete cement that we use nowadays. Volcanic ash is not really ash. Volcanic ash is actually teeny tiny bits of stone and glass, amongst other things. It's not really ash. Why it's so harmful to breathe in. Seawater. Seawater has a lot of salt and it has a lot of other minerals that's in with it as well. But you see, the Romans found out that when you mix these two together, and what they did was they would mix these three items here, and they would put it in a form, and they would dunk it underwater, and they'd leave it underwater for a few weeks. And what that would do, these two would react with each other inside the calcium oxide and all that stuff. But these two would react with each other, and they would form new binders. And they would continue to form new binders, which is why Roman cement, as it gets older, it gets harder, and Portland cement does not have anything that's creating new binders as it goes down the road. It does not. It weakens. What I have done out there cooking off calcium oxide and stuff like that and trying to figure out an aggregate and all kinds of stuff like that is I am reinventing the wheel. Bonehead move, huh? Should have paid a little bit closer attention. As you see, I thought Portland cement was clay-based. No clay in it at all. No clay. Between these two materials, I have, let's see here, 6 of the 7 materials that's in the Kastolite 30. I'm only missing a few other oxides, and I'll have to figure out why those are in there. So that got me to thinking, well, we talked about why cement breaks down under heat. Because the aggregates expand, creating microfractures. So if you've got your concrete here, and you got your aggregates, okay, and this gets hot, you got to fire it. These expand outwards. They grow because of the heat, okay? All these aggregates grow. Well, what happens if we zoom in on that? One little piece of aggregate here. As it grows, it creates these micro fractures inside the binding material known as cement. This eventually breaks down and leaves nothing for this to hold against, and it eventually just all crumbles down, kind of like Humpty Dumpty falling off the wall. Now, I hate chemistry. I can't stand it. But I seem to work with it a lot. So, this is not readily available. This is. But I don't know that we're going to go this route. Aluminum oxide, we know, is, or alumina, is an awesome, awesome, awesome refractory. The best out there. Holds up to the highest temperatures, which means it won't expand. It's an oxide. It won't expand nowhere near that, saving the cement around it. So I'm thinking mixing this and this. I think we got ourselves pretty much some Kastolite 30. Kastolite 30 has all the same ingredients as aluminum oxide. That's where your titanium oxide is coming from, your aluminum oxide. That's where your magnesium oxide is coming from in it, is your aluminum oxide. Yeah, I feel like I've wasted a couple weeks here. I just wish I would have paid a little bit closer attention. There you have it. Coming out of left field, Portland cement is a lot better than you think it is. Very close to this. Very similar to this. So, difference between alumina and aluminum oxide blasting material. This is black. Aluminum oxide blasting material is made from, I think it's pronounced bauxite. Bauxite is an ore that they make aluminum, the metal aluminum with. And they just heat it up really hot, and it turns into an oxide, and you get your blasting material there. Now, the alumina that everybody thinks about, which is aluminum oxide, which is white. The way this is made is they take aluminum, they dump it into a very strong acid rather, and it oxidizes it, and it turns it into, in which it's then later strained off, and you got this white fluffy material, which is alumina. But if they used that alumina that I'm telling you about, that high dollar acid, and the time it takes to process and the people you got to pay to do it, the price of this would be way up, and you would not have this or this. You might not even have that. Portland cement for like a 50-pound bag, I think is anywhere from $5 to $10. Kastolite 30 is I've seen it for 66. Some people say they can get it for 45. I don't think that's a 50-pound bag though. So right now we got 35. This is 5 to 10. Let's just say 10 on the high side. We got 20 here. We're already looking at $30. And if we could just use just those two things to pretty much get everything except for the alkalines, and like I said, I'm going to figure out what that's about. Because that might be where salt water comes in. But if we can, if that works, between the Portland cement and the aluminum oxide blasting material as the aggregate, and this is an insulative refractory. It goes up to 3,000 degrees. So you're looking at $30 right there, and just the time of mixing it together and putting some water to it. Versus cooking off calcium oxide, getting it right, turning it into calcium hydroxide, mixing it together with what we were going to do, and then forming it, pasting it, coating whatever you wanted to coat, and then letting it set for 7 days. It cures 7 days, but who wants to wait 7 days for something to cure